Welcome to our third and final video for modules 11.1 and 11.2. In this video, we're talking about joins. And joins get their own video because it's a super important topic. This is going to be one of the things that you'll find yourself doing most frequently. And there are 6 different types of joins we're going to be talking about. The Equijoin, which is the most common join we use. The natural join, which is just a little bit of a variation on the Equijoin. The Theta Join, which is a little bit of a weird duck and not super commonly used. And then 3 different types of outer joins. The left outer join, right outer join, and the full outer join. So join operators are signified with this symbol right here, and they are used to combine the 2 relations based on some condition being satisfied. Now in your book, the join operation is written as this X in square brackets. I suspect that's just because they didn't have the correct font to generate this symbol, but this is the symbol that you commonly see and what we'll be using in the class. So in order to join 2 relations, R and S, they must be what we call join compatible. And all that means is that there is at least one attribute in relation S and relation R that share the same domain. And hopefully this is an idea that sounds kind of familiar because this is what we said about foreign keys. All values of a foreign key must be in the domain of values of the attribute that it references. And that's exactly what we're doing here with our join operations, is joining 2 relations based on the foreign key relationship. So the general form for the relational algebra for our join operations is to have the name of the first relation, our join symbol, and we have a couple of different join symbols we're going to see, our joining condition, and then the name of the relation that we are joining to this first relation. And then the relation that is generated by evaluating this relational algebra statement is going to have a degree that is equal to the number of attributes in the first relation plus the number of attributes in the second relation. And it's going to have a cardinality, or a number of tuples, that is equal to the number of combinations of relation 1 and relation 2 where this join condition is satisfied. Now the primary difference in our join and Cartesian product operations is that the Cartesian product is going to return all possible combinations of tuples from the 2 relations, whereas the join operation only returns tuples where the joining condition evaluates to true. So when we, in the last video, looked at joining or the Cartesian product of relation C and relation D, we wound up with 72 tuples, most of which were not super useful. And we demonstrated that we could make that a little bit more useful by selecting from the Cartesian product only the tuples where this condition or this expression evaluates to true, C.decode equals D.decode. And I told you at that point that that was equivalent to doing an equijoin. So this same relational algebra expression that we already saw, we could get the exact same result by saying C join D on this condition being met. And this is just a kind of more efficient way to write relational algebra that's going to generate the same relation. And this is something that we're going to see over and over again as we're writing SQL queries, is that there are typically going to be several different ways you could write a query to get the same result. Sometimes one way is going to be easier than the other. Sometimes one way is going to be more efficient than the other, but you just have some choices there. And of course, just like with our other relational algebra operations, we can nest these operations. So in this case, we are joining relation C and D on this condition, C.decode equals D.decode. So that is going to evaluate to a new relation. And then from the relation that is generated when this expression is evaluated, we can select only tuples that meet this criteria, values of the credit attribute equal G. And that's going to create a brand new relation from which we can project only these attributes we are interested in. Okay, and this is very similar to the nested relational algebra we saw in the previous video. All right, so our 6 different types of joins, we're going to go through these step by step. First, the equijoin. So this is a join condition that is interested in the equality of 2 attributes that we're joining our relations together on. So this relational algebra expression, C join D, on this expression of equality is going to generate a new relation that has a degree equal to the number of attributes in C plus the number of attributes in D. So we had 1, 2, 3, 4 attributes in C and 1, 2, 3 attributes in D. So the resulting relation has 1, 2, 3, 4, 5, 6, 7 attributes. And then a number of tuples that equal the number of times that this evaluates to true. Okay? So the downside to this is that we do have some repetition of data. Since we're only looking for tuples where C.D code is equal to D.D code, all of the values of these D code attributes are going to be the same, which isn't super useful. So there's a couple of different ways we can fix this, we can get around this, one of which is the natural join. So a natural join is exactly like an equijoin, except it's not going to return that repeated attribute that you are joining on. So the format for the natural join looks very similar to our equijoin, except we have an asterisk here instead of our join symbol, and we get a result that is exactly the same, except we're not duplicating the joining attribute in our natural join. So there's a couple of other approaches we could take to get this same result. For example, we could do just a regular equijoin, and then from that equijoin we project only the attributes we're interested in, or we project all of the attributes except the repeated joining attribute. Okay? Or we could also do the Cartesian product and then select from the Cartesian product where C.D code equals D.D code, and then project from the relation that is generated by evaluating this relational algebra statement these attributes that we're interested in. So we have 3 different relational algebra expressions here that are all going to generate this exact same relation. Okay? And again, we'll find that when we're writing SQL code, there are 3 different SQL statements that correspond to these 3 relational algebra expressions, and they all evaluate to this same relation. So you're going to have a lot of flexibility and kind of room for creativity while you're doing this. Okay, the theta join, like I said, this is a little bit of a strange one, and unlike the equijoin, which is interested in equality, the theta join is interested in inequality. So we're looking for all tuples where the values of the joining attribute are not equal to one another. Okay, so performing this theta join, and notice that our relational algebra symbol is the same, but instead of saying where C.D code equals D.D code, we say where C.D code is not equal to D.D code. And in SQL, we represent inequality with the less than sign and the greater than sign. So that's going to result in a relation where we only have, or where we're bringing together tuples where the value of C.D code is not equal to D.D code. Okay, so essentially this is listing all of our courses and all of the departments that that course is not a part of. Okay, so that's very not useful in this particular scenario. However, there are some cases where a theta join might be useful. For example, if you wanted to run a report that was all students that haven't taken a certain class, or all of the classes that a certain student has not taken. Or maybe a list of all employees that do not have access to a certain building, or all of the buildings that a certain employee does not have access to. That's a time when a theta join might come in useful, but certainly not as often as the equijoin. All right, and then finally we have our 3 outer join operations. So when we do an inner join, whether it's an equijoin or a natural join, any tuple that doesn't have a matching or a related tuple are going to be eliminated from the resulting relation. Also, tuples that have a null value for that joining attribute are not going to be present in the relation that is created. So we can use outer joins when we want to keep all tuples from one relation or the other relation or both relations, regardless of whether they have a matching relation or a matching tuple in the other relation. So the left outer join, which looks like this, it looks just like our equijoin, except it's got these two little arms sticking out on the left, is going to keep every tuple that is in the relation specified to the left of this left outer join symbol, regardless of whether they have a matching tuple in the relation on the right side of this symbol. And then any tuples that don't have a match are just going to be padded with null values. The right outer join, same idea, except it is going to keep all of the tuples from the relation that is specified literally on the right side of this symbol, and not from the left side. And then the full outer join, where we have our equijoin symbol with the little arms on both the left and the right, is going to keep every tuple from both relations, whether or not they have a matching tuple in the other relation. So let's see what this means in our C and D relations. Now, two things I'm going to point out here. And as we mentioned in the other video, we have this architectural history course, which does not have a department. And then if we look closely at our departments and our courses, we'll find that we have one department, the philosophy department, which does not have any courses in relation C. So in this case, we're going to do a left outer join, where we say D, left outer join C on this expression of equality, and the resulting relation is going to have all of the tuples where C.D code is equal to D.D code, and then also return any tuples that are present in D, even if they don't have a matching tuple in C. And in this case, we get the philosophy department, and you see the name, course number, credit, and D code is padded with null values. Okay. Similarly, we could do D right outer join C on D.D code equals C.D code, and we're going to get all tuples from C, so we get the architectural history course, even though it doesn't have a department that it is matched up with. And then if we were to do a full outer join, so we're saying D full outer join C on D.D code equals C.D code, now we get both the philosophy department and the architectural history course. So that's it for joins, and that's it for modules 11.1 and 11.2. In the next series of videos, we're going to start looking at SQL queries and how we can write the SQL to operationalize these relational algebra expressions.